Okay, so today I was going to talk about pitch factor and distribution factor, and we'll look at it using Fourier analysis because I think it sheds a lot of light on the exactly what's going on in the machine. So the pole pitch can be defined as the circumference distance 2 pi r divided by the number of poles. So that would have units of meters, or it could be written in terms of degrees. So 2 pi divided by the number of poles will give you some degrees. So in the first design with the 6 slots, we drew up the winding function, and we got a square wave. So for the 6 slot winding, the coil pitch W was equal to the pole pitch. So if we now this comes more clear when I draw the 12 slot one. So we had for the for that 6 slot design we looked at last lecture, we had a square wave. So the location of the coils and the poles lined up. So this is, we could make this distance here TP, the pole pitch, and this distance here as the coil pitch, W. They're the same. So, but then for the, where this is angle, this would be 360. So, but for the 12 slot design, we had a different winding function. So for the 12 slot winding function, we had these 0 points in the waveform, right? So, and you can see that it repeats after 180 from this offset center point here. So so then they're not the part that is non-zero is not the same as the 180. There's parts that are 0. So we can define this difference by defining the pole pitch as being from 0 to 180, and the the coil pitch as being W. So they're different. The coil pitch W is less than the pole pitch TP. And this was the case for the 12 slot design. Okay. Now, if we look at the fundamental component from the Fourier analysis that we worked out, then we can see that the fundamental for the Whining function was given by, for the 6th slot, we had that the Whining function for the fundamental was 4 NW divided by pi sine theta. But then for the 12th slot, we had, for the 12th slot, we had that the Whining function was given by 4 NW divided by pi, and then we had the sine term here, sine 5 pi over 12 sine theta. So the effect of having the coil pitch being less than the pole pitch is that the magnitude of the fundamental is less, and we saw that. We got a slightly smaller, I think it was 9.96, the fundamental term. But we also got lower harmonics, which is a good thing. So the cost of having the lower additional harmonics was a slightly reduced fundamental. So we can characterize this, and it's important for voltage because the induced voltage, if it was a generator, would be less if the fundamental is lower. But we can characterize this using a factor called the pitch factor. Does it cover the whole width? Okay. Okay. So we can define a pitch factor that explains the difference between the magnitudes for the fundamental. So we could then define a pitch factor Kp, where Kp is the ratio of the fundamental, and I'll put a 1 for fundamental here. Actually, I could put a 1 on here too for fundamental. So we have the fundamental for the 12th slot divided by the fundamental for the 6th slot, and so that will just give us sine 5 pi over 12. And again, this analysis is based on fundamental. It's important to recognize that component. So it turns out then that for the general case, the pitch factor can be calculated from looking at the fundamental field going across the pole of the machine. So let's look at that in a little bit more detail. So let me just write in general the pitch factor can be calculated from by considering the fundamental field crossing the air gap. Okay, so let's look at what this all means. So if we just consider a two-pole machine with just a couple of windings. So if we look at that, doesn't look like a circle. Looks like a pumpkin. Let's try again. So if we have a device with two windings on it, like this, then the outer one is stationary and the inner one can rotate. Okay, then the inner one, it's going to create a field. The wires, the coil, is going to create a field that circulates, and it's going to try to couple to the outer winding. And so you can see that then the flux linkage between the rotor and the stator winding, single winding, will be maximized if they were lined up, if the angle between the two windings was 0. So in this example, we've got pole pitch, which is again the circumferential length divided by the poles, right? So it's going to be 180 degrees, and then the flux linkage in this example between the rotor and the stator, as a function of the angle, could be written as the number of turns on the coil times the maximum flux times omega, a mechanical omega m times t. Okay, so where NW is number of turns, and then this flux, this is the flux. This would be the flux over the pole. So from this winding all the way around to the other part. So from one slot to the next. So then if this is the flux linkage, then we could calculate the induced voltage as a function of rotation And so that's going to be the change in the flux linkage with respect to time. So we have change in flux linkage with respect to time. So then we could have, in the most general sense, we could have the flux changing in magnitude and the time, the omega t part changing in time. So we have, then we'd end up with two terms. We'll end up with the change in flux with respect to time times cosine omega t plus the change in the position, right? This gives you the positional change, the physical position of the rotor with respect to the stator. And so that is, the second term is the speed voltage term. So this is a speed voltage term. The faster it goes, the higher it will be. And then this term is only present, this is only present if magnitude of the flux, magnitude of the flux changes. So so if the magnitude of the flux is not changing and it's in steady state, then we can write, so in steady state where this term doesn't change, so that would mean we're not changing the magnitude of the winding field on the rotor. Then the induced voltage will just be the first term. Which which has a max value of 2 pi f nW times the magnitude of flux, or an RMS of square root of 2 of that. Right. So but ideally, what would we like in an ideal situation, based on what we've talked about? We would like the flux to look sinusoidal across this air gap. Okay, so it would, rather than being a square field flux density waveform coming off of the rotor, in the ideal situation, the flux would, the field distribution around the air gap due to the inner rotor would be a sinusoid. Okay, so then if we were to calculate the total flux going all the way around the rotor, what would it be? I mean, the flux going out must come back in, right? So if we went all the way around, it would be 0, because it should be equal and opposite. So, but if we want to know the flux linkages, just from the magnitude of this flux here, and it's a sine, the field creates a ideal sine wave, which is what the fundamental flux is, then we can evaluate that by integrating from here around to here, assuming that all around here, assuming that this field coming across that is a sine wave. So in that case, in that ideal situation, so ideally, and this is what the fundamental is when we look at the fundamental Whining function, we're assuming that the flux is sinusoidal, really. So ideally, the field crossing the air gap is sinusoidal. Then the peak flux can be determined by integrating, half of a sine. So we have across the pole a field which looks like this. So this would be minus W over 2, and this is W over 2. And so just like with the 6-slot design, and this simplified one, we just got one coil. The pole pitch and the slot pitch, the pole pitch and the coil pitch coincide. So this is pi over 2, and this is pi over 2, minus and plus. So then we can evaluate the flux. This is the ideal case. So we'd have minus pi over 2, pi over 2. So this is the magnitude here, B peak. So this is elementary, but bear with me. So B peak cosine theta L R d theta. So the L. So in a machine, you're going to have some axial length to it in a rotary machine. So the L would be the axial length here, and the R is the radius. So depending on if we're calculating from the stator or the rotor, it's the inner radius of the stator. So then we'd integrate that, and we end up with LRI B peak times 2. Okay? So that's the ideal situation, the field coming across as a sine. But what happens if now we still think about the ideal situation, but the slot, the pole pitch and the coil pitch are not aligned. So so the stator could be less than 180 degrees relative to the rotor being 180 degrees. So in that case, the amount of flux crossing from the rotor to the stator won't be from pi over 2 to minus pi over 2 to pi over 2. It will be a bit less than that. So we can calculate that. So now, what if not all of the stator flux connects with the rotor, or vice versa? So in that case, we could and for the ideal case, we're assuming the field has a sine wave distribution or a cosine wave distribution. So then, we still have this ideal case where the flux is going across in a sine, but not all of it is connecting because the stator slot, the coil pitch is different to the pole pitch. So we can calculate that by only calculating the field going across a certain amount of the coil pitch. So from here to here, this length here is TP. Remember, TP is the pole pitch. And then, but then from here, now let me make it a bit smaller. Make it a bit clearer. From here to here, this is the coil pitch. W. Coil pitch. So this is what we had. We had a difference, remember, between the pole pitch and the coil pitch for the 12 slot design, because the winding function didn't go all the way across 180. It was some 0 points. Like, we had this. So, but this was a square wave. We're just looking at the fundamental of this. So we can calculate using this what the pitch factor should be to account for this difference in the coil pitch and the pole pitch. So looking at this, then, if you look at this, then you should be able to see that the distance from here to here must be TP minus W divided by 2. And similarly over here, it's got to be TP minus W divided by 2. And this end part here is TP over 2. And so then if we make this 0 here in the middle, and then on this side at this point here it must be minus TP over 2. Maybe I'll put that here. This is TP over 2. Is that, hopefully that's clear. So let's go now calculate the pitch factor for the fundamental field going across the air gap. So we have that we have the flux going across due to the pole pitch, and the flux going across and connecting to the coil pitch. So we can integrate from minus W over 2 to W over 2 cosine pi TP x dx, where this is x here, and then we divide that by the integration of minus TP over 2 TP over 2 minus cosine pi x divided by TP dx, like that. So if we do the integration, we're going to get sines, and then we substitute in the limits. So we get sine, I'm just skipping one step, sine pi w divided by 2 TP minus sine pi 2 Tp minus W. When you do the integration, the pi over Tp and the pi over Tp that come out, they cancel. And then on the denominator, you're going to have sine pi over 2 minus sine minus pi over 2. And then if you substitute, if you rearrange that a little bit, you can use a trig identity, because you've got you can add these terms on the we don't need to add that. I mean, this is a minus here, so this can come out, and so then you end up with 2 sine pi W divided by 2 Tp divided by 2 sine pi over 2. Sine pi over 2 is commonly known as 1. So then we finally get sine. So this, remember, this is the pitch factor. Sine pi W divided by 2 Tp. Okay. Now if we, so that's for the ideal case where we've looked at a different, where we've got a difference between the pole pitch and the coil pitch. So now let's look at the winding we just, let's look at the 12 slot winding. So for the 12 slot winding, we had a pole pitch of 180 degrees, but I don't know if I wrote that down, did I? Yeah, I didn't put the values in the when I didn't put the values on the plot when I showed that. You can go back and look at the waveform. I'm talking about this one. So this is W, and this is Tp, the pole pitch. So the coil pitch is 150 degrees. So then, using this formula, we have Kp is equal to sine pi 15 divided by 2 times 18, which, then gives us sine pi, and there's a 2 here, sine 5 pi over 12, which is what we got from that Fourier analysis. We got that out, that factor, from that Fourier analysis. So what this says is that you can if you look at your winding function and you look at how the pole pitch and the coil pitch are different, you can use that to immediately find what that term is, the Kp term, in the winding. And this factor here will give you the difference from the ideal case where the pole pitch and the coil pitch are the same. So, but what this means though is that will have an impact on the induced voltage, which I think so this gives a Kp equal to 0.96. So if we go back now to where's where I wrote out the voltage. So if we go back now to the induced voltage, here, it was here the whole time. Then we could add a Kp here for the pitch factor, because we're going to get a lower induced voltage from the from this winding due to the reduction in the fundamental. So we can get that straight out using this equation. Okay, I'll stop for a brief minute, a few minutes.